I'm Nandini Shivalingam. Today I am going to explain about a topic, neon technology. This neon technology is implemented in an ARM processor. Before that, what is neon in the sense? It is a neon instruction set is a 64 or 128 bit. It is a 64 or 128 bit instruction set which is added to SIMD architectural extension in the ARM V7A profile. That is ARM V7A profile in the sense ARM is a processor and the V7 is a version of this processor which is 7 and A denotes application. So this neon instruction set is a 64 or 128 bit which is added to ARM V7A profile and it is based on SIMD architectural extension. So before that, what is ARM processor? In the sense, ARM is nothing but advanced RISC machine. And this RISC denotes reduced instruction set computing, where in this reduced instruction set, it is a CPU design strategy. It is a CPU design strategy. In this RISC, the instructions are simplified as much as possible, and here the instructions can be executed very faster, and also it provides very high performance. And in this RISC, it requires more complex coding. So there are normally in the instruction there are two types of instruction set. One is RISC, another one is CISC. That is complex instruction set computing. Here it is just opposite to the reduced instruction set computing. In this complex instruction computing, the instruction set are as much as a complex. It is only used for very lengthy and difficult programs instructions to perform. And this is about advanced RISC machine, and in this advanced RISC machine version 5 in an application profile, this neon technology is implemented, and it is mainly targeted for multimedia applications. This application of this neon is mainly in the multimedia. So when going for this advanced SIMD is also known as neon. This extension is also otherwise known as neon or a media processing engine. So it is, as I said earlier, it is a combined 64 or 128 bit SIMD instruction set. It provides standardized acceleration for any media or signal processing applications. And that's about this advanced SIMD. So before going on to the main topic of the neon, let us discuss about some things in this SIMD. SIMD is nothing but single instruction multiple data. So this SIMD is where one instruction acts on multiple data points and usually carrying out the same operation all the time at the same time. So this is using single instruction multiple data can be accessed to perform same operation. That is single instruction multiple data, and this it can be explained as it is a class of parallel computers in the Flint's taxonomy. So what is Flint's taxonomy here is? Flint's taxonomy here it describes it is nothing but a classification of computer architectures which is proposed by a person called Flint, and this Flint's taxonomy describes various flavors of parallelism here, and here it is an example which is Flint's taxonomy classification. Here this is single instruction and multiple instruction, single data and multiple data. When single instruction and single data combine to form single instruction single data, here a single instruction acts on a single data to perform a same operation. Only one thing is done here, and example for this SISD is a traditional scalar processor. And in this MISD, multiple instruction acts on a single data to perform multiple operations, and this is denoted by MISD. And another thing is SIMD. So using single instruction, multiple data can be accessed to perform the same operation at a time. That is SIMD. This is the main thing which is given in the neon technology. And this is example for this SIMD is a vector processor. for SIMD vector processor, and this is MIMD, multiple instruction, multiple data. So using a multiple instruction, multiple data can be accessed to perform multiple operations. That is MIMD. And example, so here in this MIMD, the example will be multi-core processor. Multi-core processor. So in this SIMD, data level parallelism is achieved, and this MIMD thread parallelism is achieved. So in all this SIMD and SISD, different levels of parallelisms are achieved. So main in this SIMD, data level parallelism is achieved here. So why we want to go for parallelism when we are computing this? The main thing is if we go for parallelism, so there is ability to execute operation at we can execute operation in parallel, so that there is improvement in the time and also speed. So that is the main reason we go for parallelism when we are computing. And the data level parallelism says here is, it is also known as a loop level parallelism. It is nothing but it is a form of parallelization in computing across multiple processors in a parallel computing environment, so that it can provide multiple assessments when we are doing same operations. This is data level parallelism. So when we are coming to SIMD, it describes, as I said, it is describing the multiple processing elements that perform the same operation on multiple data, that too simultaneously. So when this SIMD does this, so they exploit data level parallelism. That's about the data level parallelism. So the main reason why we want to go for SIMD is that if in some modern softwares like media codecs and graphic accelerators, so in all these modern softwares, it requires some large amount of data to operate on it. So it is less than word sized. So if we go for audio applications, it need at least 16-bit data, and for video and graphic applications, it need 8 bits of data. So when performing these operations, when performing all these operations on just a 32-bit microprocessor, so when we perform all this operation in a 32-bit microprocessor, there may be some part of computation units may be unused, and even though it is unused, it may require some, it consume more power, so that in order to use the better use of available resources, so we want to use available resources in a better way, so that this SIMD technology uses only a single instruction to perform the same operation in parallel at the same type and the same size. That is the main thing in this SIMD. So that if this SIMD is implemented, any hardware which does two parallel, two addition, if it does 32-bit addition of two 32-bit integers, instead it can perform 4 parallel addition of 8-bit. It can perform 4 parallel addition of 8 bits in the same amount at the same time. That is the thing why we go for SIMD. And this is the SIMD example. So that here this is instruction pool and it is a data pool. When the computer exploits multiple data streams against a single instruction stream to perform same operation, which may be naturally parallelized here. So see here it is instruction using one single instruction, multiple datas are accessed here to perform the same operation, and it produces the same output. This is in the case of SIMD. An example for this is the array processor or a graphical processing unit, which is a GPU. And this is the example, this is the difference between SISD and SIMD, where in this SISD, this indicates instruction and this indicates data, and finally the results are produced here. So when single instruction acts on single data, the output will be a single thing, and this will be like this. And in this SIMD, single instruction which will act on multiple data, it performs same operation and it produces same result. in multiple times. This is the result here. This is the main difference between SASD and SIMD. As I said, the example for this is a traditional scalar processor, and for SIMD it is a vector processor. So this is about SIMD, and this SIMD is this SIMD has it is particularly applicable to some common tasks like adjusting contrast in some digital image, or adjusting volume in a digital audio, or we can change the brightness of an image. These are many SIMD applications. It is particularly applicable to some audio or video applications, and so now the most modern CPU designs are based on this SIMD instructions. So they use this SIMD instructions in order to improve the performance of the multimedia use. That's about this SIMD. And so now when we are coming for when we come across for neon, what is the background of neon? This advanced SIMD extension is a neon. So the neon subsystem is nothing but this advanced SIMD extension. So this neon also uses a single instruction to perform same operation in multiple data simultaneously. That is the thing here, and it is extremely helpful when it goes for some media processing, like as I said, audio and video filters and audio and video codecs, everything. So, and also another thing is floating point. So this neon is not a floating point unit of the ARM processor, but the ARM processor has a specific floating point unit which is known as VFP, that is vector floating point. So these vector floating point and the neon are different, and they use the same register space, but it can be taken care by the compiler or a kernel. Even though it is different, it can use the same register space. That's about this VFP, and the main difference between this VFP and a neon are this neon does not support double precision floating points. So next I will say what are the data types supported by the neon. First of all, the difference between this neon and a vector floating point is it does not support double precision floating points, and the main thing is it supports only vectors. It supports only vectors, but it does not support like some advanced operations like square root or divide, etc. So this is the main difference between this neon and a vector floating point, and also this neon is not a floating point of the ARM processor. Only vector floating point is used in this ARM processor. That's about this difference between this neon and a vector floating point. So the main data types supported by the neon are neon data type. So as I said, it does not support double precision floating point, but it supports a 32-bit single precision floating point. Single precision floating point, and also it supports 64, 32, 16 and 8-bit both signed and unsigned integers. And finally, then polynomials. It can support polynomials also. So 16 and 8-bit polynomials are supported by this neon. These are the data types supported by neon. That is, it does not support double precision floating point, but it supports a 32-bit single precision floating point. Then it supports both signed and unsigned integers of 64, 32, 16 and 8 bits. Then it supports polynomials of 16 and 8 bits. These are the data types. And the main thing which began neon is the main selling point of this neon. Why this neon came into extent is because, for example, if there is a process of vector math here in the addition process, so this neon processor does that vector math in a parallel format. The example of this is if you are doing any operation for addition A naught plus B naught is equal to C naught. A1 plus B1 is equal to C naught. A2 plus B2 to C2 and A3 plus B3 is equal to C3. So this is the difference between the neon processor and other ARM processor. If this is the operation which is performed here is A naught plus B naught is equal to C naught. So the other ARM the processor except neon will do the operations like first it does A naught plus B naught and it produces the result as C naught. Then A1, then A2, then B2, then A3. So this is performed continuously. But here in the neon processor does the same operation in parallel. That is, it does all the things in parallel. A naught plus B naught, A1 plus B1, A2 plus B2, A3 plus B3. Parallelly does 4 operations and produces the result C naught, C1, C2 and C3 at the same time. So using single instruction, it performs all these operations and produces the same output. So the time is also utilized here. So this is the main difference, main selling point of this neon. That's about this background of this neon. So next we come across evolution of ARM instructions. First of all, this ARM version 5, ARM version 6, ARM version 7. These are the architectures. And first of all, ARM version 5 TE. This is the architecture which has introduced the enhanced DSP extensions. That is, and also this DSP extensions is also supported by ARM v6 and ARM v7. So this has full support in all this architecture, ARM v5, ARM v6 and ARM v7. This enhanced, the ARM has introduced this enhanced DSP extensions in order to increase the DSP processing capability in any ARM solutions. So to perform high performance applications. So this is utilized for increasing the DSP capability in ARM solutions and also in high performance application, so that it reduces, it requires only low power consumption. Low power consumption in battery or portable devices. This is the main thing we go for enhanced DSP extension, and also it has typical applications like it is used in audio codecs, networking, and extra thing it can be used for voice and handwriting recognition. Then it can be used in embedded control and MPEG4. This is entirely for the video domain, and it can be decoded using this DSP extension. And another thing is about SIMD instruction. Then ARM SIMD instructions. So first ARM version 5 has introduced this enhanced DSP extension, and the ARM version 6. This architecture has introduced some small set of SIMD instructions. So it can perform any 16 or 8-bit operations, and it is packed into a 32-bit general purpose register. And then the next thing is it performs some certain operations like it can execute some instruction twice or 4 times very quickly, so that it does not need any additional computation units for doing this process. So this is about ARM SIMD instruction, which is introduced by ARM v6, and it can perform the instruction twice or 4 times as quickly, and it doesn't need some additional computational units. Then Then we go for ARM V7 and Neon, version 7 and Neon. So this ARM version 7 has introduced full SIMD instruction, that is entire SIMD instructions, and this introduced SIMD instruction as an optional extension to the ARM V7A profile and ARM V7 R profile. This A profile is nothing but application profile, and this R profile denotes a real-time profile. These are the this full SIMD instruction are added as an extension to the ARM V7 and ARM R profile. So this SIMD instructions can be used for defining some instructions like instruction to operate on vectors. It may be some 64-bit double word registers or 128-bit word word vector registers. So this instructions can be used to operate on all these vectors, and this about this ARM V7, and it has introduced this full SIMD instruction. ARM V6 has introduced some small set of SIMD instruction which can be used to perform very quickly without the need to implementation of some additional computational units. So the implementation of this advanced SIMD extension within the ARM processor is called this Neon, and this Neon can be this Neon instructions perform ARM, and it can execute the instruction based on ARM and thumb mode. First thing is the Neon instruction can be executed in the ARM and thumb mode, and this Neon instructions can perform memory access. First thing is memory access and data type conversion, then data processing, so then data can be converted from Neon from general purpose register. These are the things which is done by this Neon instructions. And when we go for ARM V7 and Neon, this Neon unit is built as a media engine within the ARM core, and here the register file and more than 10 stage execution pipeline are used from ARM core. Register file is nothing but first of all, registers are nothing but it is some additional, it is a storage in CPU. Register are nothing but a storage device within a CPU, and it can host data and addresses. This is register. So register file is nothing but it is an array of processor registers. So register additional storage within CPU, and register file is nothing but more registers are placed in the array, that is nothing but register file, and this pipeline concept is also implemented over here. And over 100 SIMD instruction types are available in both ARM and thumb2 mode. More than 100 SIMD instructions are there in both the modes. That's about ARM V7 and Neon, and particularly when you go for Neon, it is the packed SIMD processing unit, and that is single instruction multiple data processing unit, and it has 32 64-bit wide registers. The register wide is 64-bit, and it has 32-bit, 32 register with the 64-bit wide, and it can be viewed in the dual view as 16 128-bit wide registers. So both as a view of this Neon register, it can be a 32 64-bit wide register and a 16 128-bit wide register. And these registers here in this Neon registers are considered as a vectors of elements, and it supports both signed, unsigned, as I said, 8, 16, 32 and 64-bit integers. And this here instruction can perform all the instruction can perform the same operation. Instructions perform same operation in all the lanes. Lanes are nothing but these are all the lanes, and the instruction can perform similar operation in all the lanes. Then this Neon technology is included. There is a Cortex processor also. So it supports it mainly supports Cortex A series processor, and this Neon is included in Cortex A8 devices. It has full support in Cortex A8 devices, but it is optional in Cortex A9 devices. This is about this Neon, and this Neon, so particularly Neon has 16 operations. That is, Neon supports 16 operations at the same time using this SIMD. 16 operations can be performed at the same time using this Neon based on that SIMD, and all Cortex A8 and Cortex A8 and A9 devices both has capability to store 128-bit vectors, but it can execute only 64-bit at once. This is in the case of Cortex A8 and A9. Even though it has a capability of 128-bit vectors, it can execute only 64-bit at a time. But the newer devices like Cortex A15, this is an advanced stage, and this Cortex A15 devices can execute 128-bit at once. At the same time, it can execute 128-bit. This is our main advantage of this Neon technology. In this Cortex A15 devices, it has very advantage, and this Neon SIMD, this engine, this SIMD engine efficiently processes current and future multimedia formats, and it enhances user experiences also. This Neon technology can accelerate multimedia and signal processing algorithms, such as some algorithms like it can encode or decode video and 2D or 3D graphics. It's nothing but 2D, two-dimensional view, and it is entirely based on computer, and 3D based on graphics. Graphic data. Then gaming and audio speech processing, then image processing, and telephony and sound synthesis. So in all these applications, it provides some triple times the performance of ARM v5. When compared to the ARM v5, it performs triple times the performance, and when compared to the ARM v6, it provides the performance double times in this algorithm. So this image processing and all comes under that is it color conversion or compositing, like that. And in video encode or decode, it is nothing but codec. It can be used for MPEG4 encode or decode. These are all the algorithms which is used here. And so now this cleanly architected Neon technology it seamlessly uses its own pipeline and also its own register file. As I said, register file is nothing but it is an array of processor register and also the pipelining concept also. That's about this Neon. When we come across this operand flow of this Neon, here this is an example of operand flow. Here it uses one or two source register, and there is a one destination register. This both are source register, this is destination register. Consider this both source register as Q1 and Q2 and destination register as Q0. So if any instruction is given, the instructions can perform same that is operation, same operation in this 4 lane. Here this is 1 lane, second lane, and this is third lane, and this is 4 lane. So in 4 lane has 16-bit elements. 4 lane of 16-bit elements are processed for the same operation and produces the same output. So when the instruction is given here, Q1 and Q2 takes the instruction and it performs the same operation in all the 4 lanes of 16-bit elements, and it produces the output. That output is stored as a result in Q0, that is destination register. So this operation, if you take the example operation as addition, it performs addition operation. So these are the 16-bit elements. It performs addition operation at a time parallelly in all these fields, and it produces output in all the lanes at the same time. This is about this operand flow of this Neon technology. And then we come across Neon operations. The operations which are supported by Neon are many things. One is addition or subtraction. Then multiplication, in particularly MUL or MLA process. Then shifts. Shift may be saturating or rounding. then bit field operations, then logical operations. Logical operations may be AND, OR and XOR. Then compression, reciprocal estimator step and reciprocal square root estimator step. These are all the operations supported by Neon, and the SMD instructions are supported by three things. One is vectorizing, compiler, intrinsic functions and inline assembly. This inline assembly is also called as assembler. Assembler is nothing but it is a program or instruction. It can perform, it can convert the instructions written in a low level code into a machine code, that is assembler, and using the assembler we can implement the Neon directly writing the assembly source code. So this Neon technology is implemented using assembly source code, and mainly in the assembly source code there is two GCC compiler and RVCT, that is real view compilation tools. Using both this, they use the same instruction to perform compilation, but the main thing is the difference will be in the assembler directives. Assembly directives and label formats or some command indicators used for command. These are the things in the assembler. And we come for intrinsic functions. Intrinsic functions are intrinsic data types. Everything uses the same thing which is used for assembler, but it uses some additional. It provides some additional features like automatic register allocation. Automatic register allocation and formatting. These are the additional features used for this intrinsic function. Mainly this intrinsic function, it gives access to some low level functionality using C or C++ source code. So it uses a function called interface using C or C++, so that this intrinsic functions can perform the Neon operations. Mainly there is a C function called interface. Function called interface to implement the low level functionality of this Neon using this intrinsic function. So that using this intrinsic function, it can use low level. It can find a low level architectural behavior in high performance. That's about this intrinsic function. And when we come for vectorizing compiler, it can be also denoted as automatic vectorization. So the compiler can perform automatic vectorization to implement the high performance Neon, but without using this intrinsic function or any assembler directives. So when we come for vectorizing compiler, it permits the portability of source code between different tools and targeted platforms. So when we use the vectorizing compiler, that is automatic vectorization, so there will be portability of source code between different tools and the targeted platforms. That's about this vectorizing compiler, and particularly the C language does not support the parallelizing behavior. So that we need to add some additional parts to the source code. So it provides. It provides that the vectorizing compiler does not compromises the source code when it is used for portability. That is, the portability of source code between different tools and targeted platforms is not compromises in any way. That's about this vectorizing compiler, and these are the three things which SMD instruction supports. And when we come for promotion or demotion, and the main thing in this vectorizing compiler, these three things are supported by RVDS. RVDS is nothing but real view development suite. And this real view development suite is nothing but it is some legacy solution for a software development that is using an old ARM processor. That is ARM RVDS. It has full support in this RVDS and also GCC. That is C and C++ compiler. So for all these three things, and this inline assembly, it is used mainly for us. It allows to able to vectorize the code in a low level format. That is the main thing in this inline assembly. And vectorizing compiler, it exploits SIMD operations using existing source code itself. And when we come for promotion or demotion, so the neon can use both register views in the same instruction, but it allows that double and quadrant operands simultaneously, and the operations can be long, narrow or wide. So for this promotion and demotion, the example will be for promotion, say example, as I said, the operand flow of the neon will be like this, and there will be 4 lanes. And it produces the output. So these two are 64-bit vectors, and here 16-bit element here, and it is 128-bit. 128-bit and output will be 32. So 32-bit integer in 128-bit vector, and here 16-bit integer in 64-bit vector. So the promotion in the sense, that is 16-bit, both 16-bit, when it does the operation, it will be converted into 32-bit. So the elements are promoted. But in the demotion of elements, when we go for demotion, this is 128-bit vector and it has 32-bit integer. So it performs shift. It performs shift and it produces the output in 64-bit. So 128-bit that 128-bit vector, a 32-bit integer is converted to 64-bit, 16-bit integer. So this is demotion of elements. The elements is demoted here, and here the elements are promoted. That is promotion or demotion, and it can use both register views in the single instruction. And the operation which is done here can be long, narrow or wide. When we go for a long, example will be if it is 16, it doubles the precision in the case of long. That is, if you are going for 16, it doubles the precision, like it is 16 will be doubled as 32, and it is in the case of long. When we go for a narrow, if you are using 32, 16 and 32, it offs the precision, that is, it demotes the elements to half the precision as 16. And when we go for wide, if it is 16, 32, the second operand precision will be given as 32, and this is wide. So in the case of long, it promotes the elements, that is, it doubles the precision, and in the case of narrow, it demotes the elements, it offs the precision, and in the case of wide, the second operand's precision will be given in the output. That is the thing in the promotion and demotion of elements. And next we go for pairwise operations. So in the case of pairwise operations, neon supports, that is, it works on adjacent registers and performs operations like reductions. When in this example will be, it is long and it is normal. In a long, if it is this register, it works on the adjacent register, and using that adjacent register, it performs some operation like reduction, and it reduces to form like this. This is in the case of long, and in the case of normal, the same thing, but the normal operation, what it will do is it just it reduces the precision. That is, it halves the precision, and here also it halves the precision in the normal case. That is, it performs with adjacent registers, and it performs the operation with reduction and forms like this. This is the case of normal, and in the case of long and normal. So next we go for load or store instructions. In this load or store instructions, using this, the different memory access pattern can be achieved. So load or store instruction can be used, and it can use different memory access pattern for loading or storing some formats. So this is the example, and it can use some unaligned transfers also. This load or store instruction can be used to load load from or store to any random access memory RAM or a registers. So this instruction can be used to load from or store to random access memory or a registers, and this is an example of this load or store instruction. How the different memory access pattern can be achieved over here are x0, x1, x2, and this is the allocation, and this memory access is stored by this load or store instruction will be, it can be either x0, x1, x2, x3, and different permutation can be done over here in this neon register. In the same way for the xyz, it can be like xyz, or the xyz is the same thing, or xyz. Different permutations are possible here also. Let's support this load or store instructions, and the pairwise operation load or store instructions are done in neon. And the main thing in this neon is neon coprocessor register. Neon has a coprocessor register. It has 256 byte register file, and using neon different that is two ways of registers can be allocated for this neon. The first thing is it can be given as it can be given as 32 64-bit registers or 16 128-bit registers. So the example of this will be, so this 30 to 64-bit registers are denoted by D0 to D31, and this can be denoted by Q0 to Q15. Since it is 16 and since it is 32. So first thing it will be D0 and D1, and the same thing up to D31. This are 64-bit. But when this is given for 128-bit, the resultant will be, this is Q0 and this is Q15. This is 128-bit. So the different that is two different ways can be accessed for this neon register. One is with 32-bit and another one is with a 16-bit. When we go for 32, it will be 64-bit wide, and when we go for 16, it will be 128-bit wide. And this support neon coprocessor register, and this register also enables register trade-off. Trade-off in the sense, different register views are also possible. Register views can also be different, and the vector length can also be varied. Here. So these are the different trade-offs over here, and the register bank. Neon has a 32 64-bit register bank, and this register bank can be shared by another thing. That is, if we implement both SIMD and VFP-V3, that is vector floating point version 3 and single instruction multiple data, both are implemented here. So it both can share the same register bank. This is about this neon coprocessor register. Then we go for neon optimized libraries. So the most easiest way to use this neon technology in our system is just to use a library which is optimized particularly for a neon. That is in the case of neon optimized library. And for this library, one example, that is, it is a recommended approach to use the neon technology in our system using the library. So there is a library called OpenMax DL library, and this OpenMax DL library is from Chronos, a group called Chronos group, which is a neon optimized royalty free library for AV codec, that is audio video codec. Codec is nothing but that is it is a program or instruction which is used for coding or decoding from a digital data stream or a signal, that is audio video codec acceleration. So if you want to do acceleration for audio video codec, so we can use this OpenMax DL library, which is a neon optimized and royalty free library. And also this OpenMax DL library supports many things. First thing is MPEG4 and H264 baseline. Nothing but MPEG4. The expansion of this MPEG4 is Moving or Motion Picture Experts Group. This is MPEG4 and H264 baseline. These are the standard for video compression, and this H264 is mostly commonly used format for recording or video compression. And this first thing it's come under video domain. First thing will come under video domain. And another thing it supports is JPEG. JPEG is nothing but the same thing but Joint Photographic Experts Group. This is JPEG. Joint Photographic Experts Group, and this JPEG will come under image domain. Just it comes under image domain. And next we go for color space conversion, rotates, scaling, compositing. This everything come under image processing domain. So the processing is done using one image. So this all comes under image processing domain. And next we go for MP3 and AAC. AAC is nothing but advanced audio MP3. Next AAC. This MP3 and AAC will comes under audio domain. This supports both that MP3 AAC also. Then next we at last FIR, IIR, FFT and dot product. FIR, as I said, this is finite impulse response, and IIR infinite impulse response, and FFT fast Fourier transform, and dot product. These are all the processing, signal processing domain, which comes under signal processing algorithms. So main thing, the OpenMax DL library supports all these domains: video domain, image processing domain, signal processing domain, audio domain. It supports everything. And let's support this Neon optimized library. So if we want to use this Neon system, Neon technology in our system, the most easiest way is to use the library which is optimized particularly for Neon. Then next we come across, that is Neon support with the open source community. How the Neon supports with open source community in the sense, first of all, Android. In the case of Android, it has Neon optimization also. And in Ubuntu OS, Android is that OS. And in the Ubuntu OS, in the 9.04 version, it supports Neon. And then the next thing is Blues Linux Bluetooth protocol stack. That is, Blues is nothing but a Bluetooth stack which is particularly made for Linux. And the main goal of this Blues is it should implement the Bluetooth specification particularly for Linux. Then FFmpeg. FFmpeg is nothing but fast forward moving picture experts group, and particularly in this FFmpeg, the AV codec, that is audio video codec library, supports this Neon. Then Android Scala library. Android Scala library is nothing but it is a 2D library. It is a 2D library which is used for moving text, images or graphics. So Android Scala library used. Then again to C++ vector math linear algebra. Again to is nothing but a C++ template library particularly for linear algebra. Linear algebra says it under this vectors, matrices or any some required algorithms will come under this linear algebra, and it supports this Eigen2 library also. Then Pixman. Pixman is nothing but it is an open source and a free software. It is an open source and free software which is used for pixel manipulations. Which is particularly used for pixel manipulation, for image compositing and any trapezoid rasterization. So the main worker for this pixel is Cairo 2D graphics library. It is a library which is particularly for graphics, and this is a open source community which supports this Neon. Next we come across Neon features and benefits. Main thing in the Neon is the feature will as Neon supports many widest range of multimedia codes that is used for applications, and it also supports many soft codec standards like, as I said, MPEG4 which will comes under video domain, and the real AVS H264, everything will comes under video domain. Then it is an ideal solution for any normal size internet streaming solution which can be decoded of various formats. Normally the internet streaming is nothing but it's a multimedia. It can get all the details, and it can give it to the end user. end user in a various format. So for the internet streaming, internet streaming supports this Neon also, and not just for codecs. That is, as I said, it is used for codec, that is coding and decoding process of the audio or video, and not only just for this codec, it also applicable to some 2D and 3D graphics or vector processing. As I said, 2D graphics will comes under, that is two-dimensional, whereas here the entire thing is digital images, which is computer based, and in 3D based on graphic media which we use. And then another thing is finally off-the-shelf tools and OS support and ecosystem support. When we come for off-the-shelf tools, that is COTS, commercial off-the-shelf tools. COTS, it is entirely commercial product and ready-made, and it is a standardized tool. So Neon supports all the off-the-shelf tools, and there is a OS support and ecosystem support. Then finally, before going on to the conclusion, why we go for Neon as a sense? In the sense, why we want to use Neon here is, Neon enhances many user experience. That is, it uses multimedia. It enhances multimedia user experience. Plus, it can first of all, why we go for Neon is user experience, enhanced user experience. And next thing, we can watch any video in any format. Any video in any format. Then there will be video stabilization. That is, if we want to edit or enhance some videos, we can go for Neon. So there will be stabilization for the video, and next thing is voice recognition in the game processing. And next, so it can process multi-megapixel photos very quickly. So multi-megapixel photos can be processed very quickly using this Neon. Multi-megapixel photos. Then it uses multi-channel hi-fi processing. It uses multi-channel hi-fi processing also. So the main thing we go for Neon will be the enhanced user experience. We can watch any video in any format, and there will be video stabilization and game processing. Multimedia pixel photos can be processed very quickly, and multi-channel hi-fi processing. Everything will come under this Neon. And finally, when I go for conclusion, the third-party ecosystem which supports this Neon will be many peoples. That is, first of all, I give some third-party ecosystem support. First is On2 Technologies and Adobe, Dolby, then Fraunhofer, then this On2 Technologies, then Visual On. These are some third-party ecosystems which supports Neon. So this On2 Technologies supports this Neon by using MPEG, then H264 everything. Then Adobe will be Adobe also uses some video domains, and for Dolby it will be some MPEG4 or some audio domains, and for Fraunhofer the same thing, H264 MPEG and Visual On. So everything, audio domain, video domain, image processing domain, everything will be supported with the third-party ecosystem support. For a right application, the Neon technology will give the 2 to 8x performance boost and over the right application. And since it uses pre-optimized library, there is no development tech to yield a right product using this Neon technology. And also another thing is there is a broad range of support. From many software vendors, and also there is a OS support from many OSs like Windows, Linux, Android, Symbian. So there is a OS support. So broad range of support for many software vendors, and also OS support for this Neon technology. And this neon technology uses extension. Since it uses extension, system cost will be low when comparing to the some normally used CPU or hardware accelerator. And also since it uses pre-optimized library, development cost also very low when it is compared with debugging time and developing time. So that's about this neon technology, and it has many advantages over here. And finally, as I said, for the right application, the neon application can yield 2 to 8x of the performance boost here. Thank you.